Season's greetings and Cthulhu Fountain hackers. My name is Alhazred, and I'm here today to help you erode one of our last lines of defense against the machines, the almighty CAPTCHA. That's right. The machines are taking over, and I, for one, welcome our new ChatGPT overlords.
Guess the language in the following sentence. Sorry, I cannot guess the language without the sentence. I cook a pizza. The language appears to be Italian.
CAPTCHA, which stands for Completely Automated Public Turing Test to Tell Computers and Humans Apart. That's a little bit of a mouthful. No wonder they abbreviated it. Is essentially ubiquitous across the internet these days and is predominantly leveraged in various forms by websites such as at login portals to make sure it's a human logging in and not a program or a script. Ideally to prevent brute forcing and other forms of automated attacks. Obviously, this is a problem for us red teamers, practitioners of the dark arts, because if I want to brute force a login prompt, that pesky CAPTCHA is going to be a thorn in my side, using like my Hydra or my burp intruder or whatever. Fortunately, although CAPTCHA are designed to keep the machines from accessing these forms, ironically the answer is actually machines, but a little cleverer. This video is going to show you how you can leverage neural networks and machine learning to bypass CAPTCHA restrictions. Hopefully, the skills you learn here will still be applicable when SkyNet takes over and CAPTCHAs are actually designed to allow machines to log in and deny humans. What would such a CAPTCHA even be like, though? Honestly, being real with you for a second, I'm really just doing this room for my own benefit because I don't know about you, but I probably fail those CAPTCHAs more than actual machines do. I'm hoping this room will give me some tips, such as on whether or not a traffic light includes the pole the light is mounted on, which is a question I've had for half a decade at this point.
Not sure what that has to do with jaywalking, but okay. What? Congress people in bed with lobbyists. Maybe these guys? Oh, okay, that didn't... Alright.
The good news, well, it's good news if you're just trying to finish your daily Advent of Cyber challenge. It's bad news if you're trying to prevent a machine apocalypse and the extinction/subjugation of the human race to artificially intelligent emperors, is that the practical application of this task is actually very simple. Most of the work has already been done for you. You can solve this challenge with literally, I think it's 4 terminal commands if you so choose. I'll drop a time code in the description for those who want to jump to the bare essentials. Obviously, I'm going to recommend that you watch the entire video because I will be going through the steps and explaining everything in such a way that is hopefully easy enough to understand that a beginner can grasp the concepts. This challenge might seem a little bit intimidating with the way it comes at you hard with scary words like feature extraction and convolution, but do not feel like you need to fully digest and understand each of these. The goal is not to make you a machine learning savant in just a few short challenges this month. It's to give you a high-level understanding of these concepts, how these systems can be leveraged by an attacker, and the resources to learn more if you choose. The goals of this video are the same, to deliver high-level understanding so the next time the topic comes up, you'll be able to talk intelligibly about it and know where to start if you want to learn more. So let's hop in. I'm not going to go through all the lore from the actual task with you. You can all read. Although, if you're a member of my Twitch chat, that assumption isn't necessarily valid. But the point is, for most of you, I'd be boring you to just regurgitate that information. Rather, just like on my Twitch stream, we're going to learn by doing. Let's get our hands dirty, get into the command line, crack open some ancient tomes, and start meddling in forces scarcely within our comprehension, and which could very well begin the downfall of the entire world as we know it. Let's get started. So the first step, as with most of these challenges, is to start the machine. You're definitely going to want to use the provided virtual machine because a lot of things have been set up for you ahead of time, including all the required software and the necessary training data, and things are going to be a great deal harder and more time-consuming to do from scratch. You just come up here, you click on Start Machine, and you wait for it to open. I'll jump the video forward to when mine loads. So here we are in the virtual machine. Before we get started with the hacking, let's just take a look at the target. If you click on the Firefox icon on the right, Firefox should open up and it should go right to the page in question, which is at hqadmin.tryhackme port 8000. You can see we have a fairly standard login page here with the promised CAPTCHA right there in the center. This is a fairly simple CAPTCHA, but the principles we're going to be exploring today can be applied to more complex CAPTCHA as well. So if we try a simple username password combination and then just some gibberish for the CAPTCHA, we do see that it correctly rejects our login attempt due to incorrect CAPTCHA. Sometimes you will run into web pages that aren't just not checking the CAPTCHA, but this one appears to be effectively preventing machines from guessing passwords at first blush. You'll soon see, though, that it is no soldier from the future.
Just let me go. Listen and understand that
TensorFlow
is out there. It can't be bargained with. It can't be reasoned with. It doesn't feel pity or remorse or fear, and it absolutely will not stop, ever, until you are
logged in.
TensorFlow is an open source software library developed by Google for machine learning and artificial intelligence, and you are going to use it to bypass this CAPTCHA. This is its main webpage, which I'm showing you mainly so you know where to go to learn more about it if you'd like. We don't really need this page open for right now, though. For simplicity, this task uses Docker containers to handle all of TensorFlow's dependencies. If you don't know what Docker is, don't fret. Grasping the complexities of Docker is beyond the scope of this task. For our purposes, understand Docker as kind of an isolated mini virtual machine inside of your TryHackMe virtual machine. It's often used for running single applications with a lot of complex and specific dependencies, like this one. It's a really convenient way to bundle an application together with everything it needs and keep it from conflicting with any other applications. You can start the container thusly. Docker run tacd tacv, and we're going to use the temp data directory for our shared folder, tempdir for the mount point, and then aocr/full. Okay, so to briefly explain this command, here we are using the Docker client to run the aocr/full container image. Since the Docker container is its own isolated environment, our virtual machine cannot access the file system of the container directly because it's a whole separate file system. That's what this tacv option is for. We are essentially creating a shared folder. We're establishing the /temp/data directory on our virtual machine as a folder that is mounted inside of the container at we just gave it an arbitrary mount point of tempdir so that we can share files between the two file systems. The tacd option tells Docker, hey, just run this container in the background. I don't really need to see output from it. If you get this long hexadecimal gibberish, it's a success. Your container is running. You can copy this and use it in the next command, which is going to be docker exec tac-i tac-t, and then the container ID /bin/bash. So this command is essentially telling Docker to connect to the container we just started and execute a particular command. That's what docker exec is used for. The tac-i option puts the Docker client into interactive mode. The tac-t option allocates a sudo tty for the container, and /bin/bash executes a command shell. And you can see that our command prompt has changed here because we're now inside of the container isolated environment. Once you're inside there, you can cd into the /ocr directory, and we're ready to go. This is the directory we're going to be operating out of for most of this task. Now, let's briefly talk about what we are about to do. AOCR stands for attention-based optical character recognition. It is a TensorFlow model for training image recognition neural networks. It's essentially a model for training a neural network to recognize images similar to the way your eyes do, hence optical character recognition. You can find out more about it at its GitHub page, link in the description down below. The specific type of neural network we're going to be using is a convoluted neural network, and you can read more about that in the lore of this task at your leisure. As I said earlier, much of this task has already been done for you, and this is not because it is hard necessarily, but rather because it takes a lot of time and or a lot of computing resources, which we don't have in this virtual machine and I don't have in the runtime of this video. I will quickly summarize the process so you know how it works, you know where to start if you'd like to experiment more, and so on and so forth. The first thing you need is training data. In this case, we need a lot of examples of the CAPTCHA we're targeting. You could theoretically use other pictures of letters to train your optical-based character recognition neural network, but you'll have the best results, obviously, if you train it on the specific CAPTCHA that you're trying to target. So if we go to the main page again, you can see that every time we reload the page, we get a different CAPTCHA. Obviously, it's how CAPTCHA works. So we can gather training data. The most efficient way to gather training data is probably going to be programmatically using something like curl. It was hq_admin.TryHackMe port 8000. And all right, let's scroll up. And if you see all of this base64 encoded data that I'm scrolling past, this is actually the CAPTCHA. This is the raw binary image data of the CAPTCHA. So the best way to accumulate data might be to use a script that'll send a request to this login page, extract the CAPTCHA image from the response, display it to a user so that they can provide the correct answer, and then store the image in a particular directory while adding a reference to it in what's called an annotation file, along with the answer to the CAPTCHA. You then do this a few dozen, 100,000, 10,000 more times, and boom, you're ready to create SkyNet for this specific CAPTCHA, that is. As mentioned, the above is actually quite easy to do, but it's kind of a pain and it's time consuming. So it's been done already. You're welcome. Check out the data in this subdirectory if you would like. It's in the raw dataset directory. Now, this might take a moment to load because there are thousands of images in here and Bash has to catalog them. In this case, the CAPTCHAs in the login prompt were generated using the CAPTCHA Python library. So you'll also see the script that was used to generate more CAPTCHAs for training the neural network in this directory. And that's this right here. And you can see the literally thousands of other image files in here, all labeled by presumably what the answer to the CAPTCHA is for convenience. So if you're wondering where the annotation file is, you can view that at labels training.txt inside the labels directory. The head command by default will only show the first 10 lines of this file, but there needs to be a new line in this file for every image that we intend to use to train our neural network. You can see it has a path to the image relative to the raw data directory, and it has the answer to the CAPTCHA associated with it. Now, we need to use these files to generate a training record that TensorFlow can use to train the neural network. This sounds complicated, I know, but really we're one command away. So aocr dataset, we're going to provide the annotation file, labels training.txt, and just a file to save the TensorFlow records, so training.tf records is fine. Again, this has been done for you, so don't feel like you need to for right now. I'm going to skip it for time purposes. And also, adjust my terminal window so that the command isn't cut off in the future. I apologize for that. I'll up arrow so you can see the command if you're interested. It's aocr dataset ./labels.training.labels training.txt. That's the annotation file, and then the file in which to save the TF records file. So now we're ready to train. Okay, we're ready to go ahead and train. So let's go ahead and cd into the labels directory. Now you might think that training sounds complicated. Training a neural network, that's a lot of fancy words, so that has to be complicated. We're not in a Rocky movie where we can just cut to a montage and get to the end.
We're gonna need a montage. A sports training montage.
Would you believe me, though, if I told you it's actually easier than that, because we're just one command away from training the neural network at this point. So we can just do aocr train labels, and then the, I'm sorry, it's in this directory, training.tf records. This is the part that really will take a while, given the limited computing resources available in this virtual machine. I'll let it run here for a minute or two while I explain things, so you can see what the output looks like, and I can horrendously bastardize the complexity of what is happening here for hopefully so that a beginner can understand. So it's easy to get a computer to recognize a single image, obviously. Ultimately, all the image is ones and zeros. Images of numbers are no different. An image of a number 6, it's all ones and zeros. Each pixel is a byte or a series of bytes that are interpreted as colors by whatever software is displaying the image. Matching images is as simple as comparing the bytes to see if they match. The trick is getting the computer to recognize a similar but not identical image as related to a different image. An example of this is the number 6, an image of the number 6 in 2 different fonts. The 6 is going to look slightly different in each font, but we, as human beings with our eyes, understand that it's still the number 6, and we need the computer to recognize that they both mean the number 6. As mentioned earlier, TensorFlow is a convolutional neural network, or CNN. And when you train it like we are right now, it's taking each image and dividing it up into a grid, with each square on the grid being a group of pixels in the image. It summarizes each group of pixels with a single value and then combines all of the values in the image and does some more math to learn that this particular group of values is associated with a particular image or idea. In this case, a number, the answer to the CAPTCHA. We're teaching our CNN what particular group of values, generally speaking, looks like the number 6. This CAPTCHA only has numbers, but you could do this with letters as well. It's going through our entire data set. With every one of these steps, it's going through our entire data set, thousands of images, and it sees different versions of the same numbers. The more data it is exposed to, the more variations of 6 it sees, the more likely it is to recognize a new 6 that looks a little bit different. And since you're also including the number 9, it also needs to learn that these are actually different numbers and not the same number in a different orientation. And that adds additional complexity as well that is ironed out in the training process. And also, what if it sees those next to each other? It won't even know that 69 is nice. So we have to teach it that too. Obviously, this is a ridiculously oversimplified explanation. You can see a more in-depth one, but still fairly simple, in the task itself, and I deeply encourage that you read that because it does a better job of explaining it than I probably just did. So this, again, is going to take a really long time, and it's already been done for you. So go ahead and Control-C out of this after you see a couple of these steps. I just wanted to show you what the output looked like. It takes this long, remember, because TensorFlow is literally going through the entire data set, thousands of images, and doing all the stuff we just talked about for every single step. And it's doing it in an iterative sense and getting a little better every time. If it ever ends here, I can move this up. There we go. I'm just trying to make the terminal a little bit bigger so that we can see the so you can read the output here a little bit better with this huge font. So for reading this output, each of the steps of the training is another iteration. You can see a timestamp of when it was started, the user that did it. You can see the number of steps that were on. You can see how long it took. And the important values are the loss and perplexity. Okay? So loss is how often the CNN chooses incorrectly. How often it gets the CAPTCHA wrong. We want that close to 0, which we can see that it already is. Perplexity refers to how sure the CNN is when it's making its guess. We want this close to 1. Close to 1 indicates it's quite sure. This CNN has already been trained, so you'll notice that, again, loss and perplexity are already close to what we want them to be. If we were training a fresh neural network from scratch, these values would start out wildly different and would gradually get better over the course of the training process. So, our neural network is trained now. I'm going to make this a little bit bigger again, because I think it's a little bit more convenient this way. There we go. So, SkyNet is online, gamers. But before we actually just fire it off on our target, we should test it, right? So we have a whole separate data set available once it's trained to test and see how well our neural network is doing. And we can do that with, again, just a single command. aocr test testing.tf records. This TensorFlow record file was generated in the same way as the other one, just with a different data set of new CAPTCHAs that the neural network has not seen. Okay? So what you're going to notice quickly here is that the output is going to come much faster. Once it's trained, the neural network can operate really quickly on single images. For every step that you're going to see, the CNN is only looking at a single image and making a guess as to the answer in the CAPTCHA. You can see we're going way, way quicker here. So I'm going to go ahead and cut that off. The output is very similar to before, but with a few notable differences. We can see the accuracy field now. The accuracy is 99.52%. That's how often, obviously, well, you can probably guess, that's how accurate the CNN has been across all of its steps. That's how often it's gotten the answer correct. The probability, it's how likely it thinks it is to get the correct answer based on its perplexity. You can see the probability is pretty high, but if we scroll up, we can see one where it's lower, and that corresponds with a higher perplexity. It's because for some reason that CAPTCHA was a little bit more challenging for our CNN. And we want to, sometimes the CNN guesses wrong. That's why the accuracy isn't 100%. We need to factor that in to our brute force attempt as red teamers. So an incorrect CAPTCHA probably is going to produce a log, so we can reduce the amounts of logs that are generated by simply tossing out any CAPTCHAs that the CNN isn't really sure about. So, and then we can just get another CAPTCHA and try again. So we're going to want to write that in for OPSEC purposes. Speaking of, we're almost to the actual brute forcing, I promise. We're almost there. So we need to perform the following tasks to brute force this login page. Firstly, we need to establish our CNN at a web API which can receive the CAPTCHA images and return the answers. Solve them and return the answers. Okay? Second, we need to programmatically browse to the login page, retrieve a CAPTCHA image. Third, we send the CAPTCHA image to our hosted CNN. Fourth, the CNN solves the CAPTCHA and returns the solution to us. 5, we evaluate the perplexity and the probability of the answer, and we discard the CAPTCHA if the CNN is not sure enough, and we just return to step 2. 6, once we get a CAPTCHA that we're sure about, we submit the CAPTCHA along with the login attempt. And 7 is to repeat that process until correct credentials are discovered. The first of those we will do ourselves, and numbers 2 through 7 will be done automatically by a Python script. Fortunately, we already have a script which will do all of this for us. All we need to do is host the trained CNN and then launch said script. All right? So, the first thing we need to do is we need to copy our trained model out of the Docker container so we can make use of it. So, let's go back into the OCR directory and let's copy recursively the model directory into our tempdir. Remember that shared folder we set up when we ran the Docker container? That's what this is for. We're basically transferring our model to the virtual machine so that we can use it outside of the container. Now we're basically done with this Docker container. We can exit out. And if you'd like, you can go docker ps. You can copy the container ID and do docker kill with the container ID, and it'll terminate that container for us because we no longer need it. Now, we're going to run a very similar Docker command to run a different container, but this one is going to run the TensorFlow web server so that we can host our CNN and interact with it using a web-based API. So, very similar to the command, to the other Docker run command that we saw, with some key additions. The TACP option here is setting up port forwarding. It's essentially opening up port 8501 on our virtual machine. Scroll back up so we can see the command. And connecting it with port 8501 inside of the container, which is the port on which our web server is going to be listening. Essentially, it allows our brute force script to talk to the CNN that it needs to in order to solve the CAPTCHAs. TACV is another shared folder. We're just making our trained model, which is now hosted on our virtual machine, available inside of the Docker container. And the TACE option is establishing a necessary environment variable inside of the container. You see a lot of output here. Once you see entering the event loop, you should be good to go. We can check by trying to browse to it. So it's going to be located at localhost 8501, and I think it's v1/models/OCR. Okay? You should see some JSON data in the response, and the state should say available. If you see that, you're good to go. Your CNN is now listening for CAPTCHAs that it can be provided to solve. All right? Now, we're finally there. The time has come. The brute force script is already ready. It's already been written for you. It's in the desktop. It's on the desktop in the brute forcer directory. You can see it's a Python script, and you have a password list here for it to pull from. I'm not going to waste time going through this entire Python script right now. The entire text of the script is in the task description if you'd like to go through it, and it also explains what the script is doing. And I also went through basically what the script does a little while ago. So we're not going to worry about that here. You can just execute this with bruteforce.py. And it'll take a moment to spin up. But you're going to see that just as designed, we are successfully brute forcing this login prompt. And you're seeing that if you might not be able to see because the output's going really, really fast. But you can see that we are getting some moments where the probability was too low, so we discarded the CAPTCHA and we just got another one. And whenever we get a CAPTCHA we can successfully solve, we submit an attempt at the password, at the admin password, and eventually we do actually get the password, which is really not going to guess this. All right? So now we can take that and go back to the web page. We can go admin. Really not going to guess this. Put the CAPTCHA in there. And then we sign in. Incorrect CAPTCHA value supplied. Oh God. Who's really the robot here? Damn, now I'm feeling like Domhnall Gleeson from Ex Machina. I'm about to hop off camera and cut into my arm to make sure I'm not actually a robot. Let's refresh the page just to make sure. Okay. Okay, let's get it right this time. Is that a 7 or a 1? Who knows? 79735. Are we gonna get it this time? We still get it wrong. So legitimately, I am doing worse than the CNN at this point. I am statistically doing worse. I don't know if that tells us how powerful neural networks are or how bad I am at CAPTCHAs. And we finally do get it, though. Access granted when we get a flag. CAPTCHA can't hold me back. So for answering the questions posed by this task, most of the answers are actually in the text of the task, which I deeply recommend you read. There's a lot of great information in there. But the answers are: what key process of training a neural network is taken care of by using a CNN? That would be feature extraction. What is the name of the process used in the CNN to extract the features? That would be convolution, because remember, this is a convoluted neural network. What is the name of the process used to reduce the features down? That would be pooling. What off-the-shelf CNN did we use to train a CAPTCHA cracking OCR model? That was attention OCR, the attention-based optical character recognition model. What is the password that McGreedy set in the HQ admin portal? That was really not gonna guess this. And then the flag, I'll just copy out of my notes here. CAPTCHA can't hold me back. Submit. And then the last one is a gimme. If you enjoyed this room, check out the Red Teaming Learning Path. TryHackMe has all kinds of great learning content for offensive cybersecurity. Deeply recommend you check that out. I do rooms from that path on my stream all the time. And there you go. We're done. We've finished day 16 of Advent of Cyber 2023. So there you have it. I hope you enjoyed and learned from this video, friends. I stream red teaming and offensive cybersecurity content on Twitch multiple times a week, so check me out there if you'd like to see more. For now, I'll just wish you a very happy holidays and urge you to keep hacking and adding brain wrinkles with Advent of Cyber. Cthulhu Fountain.
Hey, want to hear the most annoying sound in the world?
Like and subscribe.